Good evening, ladies.
Good evening.
I have the short introduction biography which you sent me, so don't be too critical because you wrote it.
It's all right.
So, in no particular order, Dr. Emma Daffern, if that's the correct pronunciation, final year PhD student at the University of Sheffield, and has previously investigated the way in which star clusters evolve as fractals over time. He's now focusing on the effects that star-forming regions can have on the planets within them. She finished her Master of Physics in Physics and Astronomy at the University of Sheffield 3 years ago, and is planning on leaving academia to work as a data scientist. And then we have Dr. Christine Schoettler. Is that your correct pronunciation?
It's close enough. It's a German name, so it's
Thank you. How would you pronounce it, please?
Schoettler.
Schoettler, right.
Schoettler, yes.
Thank you. So she's a final year PhD student at the University of Sheffield, and her work focuses on star formation and what we can learn from young star forming regions using simultations and observations. She came to astronomy late in life after working in industry for 15 years until 2017. Studied physical science for her Bachelor of Science at the Open University via the distance learning from 2009 to 2014, and studied astrophysics for her Master of Science at Liverpool John Moores University via distance learning from 2015 to 17. She started her PhD full-time at the University of Sheffield in 2017 and will finish it in 2021 and will continue working in academia. So please all welcome in a Mexborough and Swinton astronomy way our two guests for tonight, Emma and Christina.
Thank you.
So thank you. Is it okay if I start?
It certainly is okay.
So me and Christina have quite closely related research areas because our supervisor's the same. So we're going to be giving a joint talk on both of our research. So we'll start off just with a general introduction that applies to both of our areas of research. Firstly, starting with how stars and planets form, as well as where they form, and how we investigate these star-forming regions. Then I'll talk about my research, about is there a star and planet in our solar system, and then Christina will finish with what ejected stars might tell us about star-forming regions. So I'll just pass on to Christina for the first bit of the introduction.
Thank you, Emma. So I'm going to start our talk this evening to just give a brief introduction how stars form, to just set the scene for the talk that we give later on. And these two little comic strips, especially the one on the left here, kind of neatly illustrates in a very couple of steps how stars form from dark clouds of molecular gas. So this gas is not homogeneous. There are overdensities and underdensities, and these dense cores here that are illustrated in black will actually be the locations where stars form. In these denser cores, the star formation process starts with these cores collapsing in on themselves and getting hotter and hotter in the center. And after only about 10,000 to 100,000 years, a protostar forms at its center. This is not yet a star, as we know our stars to be, like the sun is one of these stars who started as a protostar. And the protostar is still surrounded by part of this gaseous envelope, which we can still here see the little shades of gray color. But due to the protostar rotating very quickly, a disk forms around this protostar that we can see here. And there's protostellar outflows in each direction, which go up and down alongside the polar axis of the protostars. As a next step in the evolution, this protostar turns into something that we call a T Tauri star, where the envelope, the gas envelope, actually completely disappears around the star, and the disk evolves further into a protoplanetary disk. which is rich in gas and which actually feeds the central star with more material while the star continues to grow. And this, just finding my mouse, this can take up to 3 million years. So these T-Tauri phase will go on from 100,000 to about 3 million years. And it then becomes a pre-main sequence star. I will briefly explain main sequence in a second using the cartoon on the right, but we'll show that the gas-rich protoplanetary disk eventually runs out of gas and can turn into a debris disk, which is like leftover material, little grains that form, but also planetesimals or even an infant planetary system that could have formed already here. If the disk has not been destroyed, so it doesn't mean that around each star there's a disk with debris and planets, because there's so much interaction going on in the center of clusters where these stars form that these disks don't always survive. If they survive, after about 50 million years, we'll actually see something that resembles a young stellar system with a central star that might be then already on the main sequence where it will spend the rest of its life, and a planetary system, luckily, if it has gone around. On the right, we see here a diagram, which is one of these central diagrams in astronomy. It's the Hertzsprung-Russell diagram, also called color magnitude diagram, because it links the magnitude or luminosity or brightness on the y-axis, with brighter stars being further up, fainter stars being further down, to either the surface temperature or the color, with bluer stars here, more redder stars on this side, or stellar or spectral types. So there's a couple of different things that can go on the x-axis here. We can see here that when a star forms, the clump of gas that collapses in on itself will start at a very low temperature, so really far on the x-axis and at a really low luminosity. But when it starts collapsing and the protostar starts forming at the center, it actually increases in temperature and increases in brightness. And eventually it will approach the main sequence, which is this band that spans all the way through the diagram from the top. So the younger stars will always be located above the main sequence, and the star, once it settles into its main lifetime setup, will approach the main sequence from the top. Our sun is located around here. It's a G-type star, so it's around here. And further up on the main sequence are the bluer and the brighter stars, which burn bright and die young. They're like little rock stars who go briefly through their phase and burn very quickly. And these stars above 8 solar masses will end their life very different than stars that are further down on the main sequence, because these stars up here will actually explode in a supernova, where stars like our sun will not explode as a supernova. It will expand into a red giant and will eventually turn into a white dwarf and be eventually located somewhere down here. But we will see this color magnitude diagram later on when I talk a little bit about my work. But I will hand over now again to Emma to talk about planet formation.
So yeah, as Christina was saying, planets form from the disks of gas and dust that orbit around stars as they're still forming. So this is an image of probably the most famous protoplanetary disk. There's lots of gaps in it. These might just be formed by instabilities in the disk that can cause resonances and make gaps form, but it's also very possible that there's planets forming in some of these gaps. The exact mechanism by which things become big enough to be planets within the timescale that they need to is still a bit not quite agreed on, but the basic mechanism is just that dust particles and sort of dust bunnies either stick to each other with electrostatic forces or tumble through the disk in the turbulence, just sort of gathering material until they're big enough to attract and stick to each other under gravity, where they can form objects like this. So this on the right here, you can see several different protoplanetary disks. They're in a star-forming region, which I'll talk about in a bit, but they're actually being illuminated by the massive stars in the star-forming region. So this, before we could take images like this is sort of how you could image protoplanetary disks when they were being swept away and illuminated by massive stars. So those sort of star-forming regions, like in that picture, broadly form into two categories. So firstly, there's the bound clusters. These tend to be really massive with lots of stars, and they'll be quite dense with all the stars quite close together. So just for reference, you could fit a whole cluster of thousands of stars within the distance from the sun to the nearest star to it. So within around a parsec or around 3 or 4 light years, you could fit thousands of stars. And that means that they're all close enough together that they'll be interacting with each other and flying past each other. And the stars very much don't evolve in isolation, they all affect each other. But then you also have these unbound associations. So whereas the bound clusters are massive enough that they're held together quite well under the gravity of everything that's within them, the unbound associations are normally sort of either flying apart quite rapidly, or they might just be drifting and slowly dispersing apart. So they'll tend to either be less massive, or if they are as massive, they'll be a lot less dense. Everything will be a lot farther apart. And this is where stars sort of don't interact with each other as much when they're forming. So I'll just pass that to Christina now.
Yes, so we've now heard how stars and planets form, where stars and of course also planets form. So how can we investigate star-forming regions? Because what we see in the pictures on the previous slide, bound clusters and unbound associations that we see in the night sky at this time in the astronomy life, is not actually how these star-forming regions were born. So just because we see something in a certain way, it doesn't mean that it always looked like this, because we know from theoretical modeling that many of these star-forming regions undergo quite a bit of dynamical evolution. And in order for us to understand and really pinpoint how star formation really occurs, we need to know the locations of star formation when star formation started. And in order to investigate this, we can look at observations of star clusters today in the night sky, but we need a theoretical background to understand how these star clusters formed and how they evolved over time. And for this, we use simulations we feed models of star formations into these simulations. We let them evolve over time and then see if the end result of the simulation resembles things that we can observe in the night sky. And there's two main simulation types that are used to simulate different aspects of a star cluster or star-forming regions, the evolution. You would hope that at some point in time we can actually put everything in one single simulation, because of course things that we simulate in these two different types of simulations actually happen together. But even though computer systems and all these software and hardware has evolved quite rapidly over time, we can't still put everything that we need to simulate a cluster into one single simulation software, because it wouldn't actually run anywhere. So one way to simulate the formation and evolution of these clusters is called a hydrodynamical simulation. And these study the collapse and fragmentation of a molecular cloud, which is represented here as a big a blob of red gas in this way. And then the formation of stars within this cluster. I'm going to just run this. It's like it's like image of a simulation. We see very quickly that this gas, this blob of gas, doesn't actually stay homogeneous, but that we see yellow areas of overdensities forming, which are actually called filaments, which are denser regions, are actually the areas where star formation happens, where the denser cores collapse and start forming stars. We can see one flying away here. We can already see stars forming in other overdense regions in this filamentary region. We can also see that several of these stars in the simulation do not actually stay in the cluster center, but actually start distancing themselves from their birth region really quickly. But we can see also that over the simulation time, I think it covers about a million years, that these filaments where the star formation was distributed in the space actually start collapsing in on each other, and eventually all end up forming a fairly centralized spherical region in space where we see loads of stars within the cluster and only a very little amount of gas that is left in the surrounding areas. So this is one of the ways we can use simulations to try to understand star formation. But as soon as the gas disappears from these regions, actually some different interactions take over, and they cannot be represented in hydro simulations anymore. Here, at this point, Nbody simulations come into play, which are multi-body simulations where you study only the gravitational interactions of particles in dense, dynamically evolving systems where you can put a time period on, which is perfectly suitable to simulate stars in the star-forming region. I'm going to briefly or shortly set off the simulation, but just want to explain what we see here. So this is an XY perspective, so we see something on the sky of a number of stars. I think there are actually 4,000 stars in this simulation. We see a couple of red points here, which represent the higher mass stars, which are in this simulation actually stars above 8 solar masses, which I mentioned previously already evolved differently than the lower mass stars, as these red blobs actually go supernova at the end of their life. I think there are about 20 solar high mass stars in this simulation compared to about almost another several thousands of the smaller lower mass stars. And we can see that they have a clumpy appearance because they are distributed along the filaments that we know are the locations where stars form, and they're not homogeneously distributed in the volume of space we see here. If we set off the simulation, we can see that stars fly away, they're ejected very quickly, the cluster collapses in on itself, and after only a brief period of time, this cluster, I'm going to see it in a second just zoomed out, does not really resemble much of what we saw just 2 million years ago. I'm just going to pause it here. So we can see that this cluster looks very different to what it actually started as. So just because we see this kind of cluster now in the night sky doesn't mean it looked like this when it was born. We can see that quite a lot of the massive stars actually start moving to the center of the cluster. This is actually called mass segregation, where higher mass stars move towards the center and the lower mass stars are still distributed all across the sky. We can see here high mass stars also leaving their birth region. And this kind of evolution continues then for the, oopsie, wrong direction, for the next couple of million years. What are the aspects that we can set in our simulation? Both Emma and I, we work in the same region with Nbody simulations, and there are two key aspects that appear to play quite a big role with the evolution of star-forming regions. One of this is the kinematic structure, which is represented by the Virial ratio. The Virial ratio is the ratio between the total kinetic energy, which is driven by the velocity, by the movement of the stars, in relation to the total gravitational potential energy, which is almost purely driven by the mass of the stars. We have a virial equilibrium, which I usually call happy clusters, where the kinetic energy in a cluster is completely balanced out with the gravitational potential energy. And these clusters, unless there's some external factor influencing these clusters, will not move away from virial equilibrium. But we can also set off our clusters in a sub-virial initial virial ratio. So these clusters actually start, for example, at a 0.3 virial ratio. So they have less kinetic energy in relation to their gravitational potential energy. So this kind of cluster is not balanced out. When we set off these kind of simulation, the first thing we see is the gravitational potential energy will actually cause the cluster to collapse in on itself. So the stars get closer and closer together to each other and start interacting more with each other, which will increase the kinetic energy in the cluster, which then causes this virial ratio to rapidly shoot up and even go past the virial equilibrium here to a subvirial ratio. So it will collapse in on itself and then start expanding again after it undergoes the collapse. However, it will then try to attain equilibrium because, of course, happy clusters are happy when they're virialized. So usually clusters will try to settle themselves on a virial equilibrium, which is shown here after already 1 million years that the cluster is starting actually to settle into equilibrium. The virial ratio also plays a part in what we call either bound clusters or unbound associations, because bound clusters are clusters where the global virial ratio is below or equal to 0.5, whereas the unbound clusters or unbound associations have virial ratios above 0.5, and they're called supervirial. Looking at the kinematic structure is only one of the key ingredients that we put into our simulation, and Emma is going to talk about the next ingredient.
So that's the spatial structure, or the spatial substructure, as well as the kinematic structure. So you probably saw before in the other images, but you can also see in this one that star-forming regions are really quite clumpy, and we think that they may be fractal. So this image at the top here is, I think, probably the most famous fractal. It's the Mandelbrot set, and it shows really nicely that a fractal is something that no matter how much you zoom in on all of the different scales, you see the same basic pattern or the same basic structure. And it's this that we think star clusters either are actually definitely fractals, or just that fractals are still a very good way of sort of mathematically modelling the structure and substructure within them. So fractals are seen a lot in nature, so it's definitely not unreasonable to think that star clusters might be. This is an example of it in a cauliflower. You can see that obviously in nature, in reality, compared to just a mathematical fractal, that there obviously is some sort of scale that you get down to when you can't zoom in anymore. But I think it's still pretty convincing that this is a fractal. And that means that simulations of fractals are used for a massive amount of things for simulating nature, including CGI clouds, mountains, sea. Basically everything that you see in films is probably done with a fractal if it looks realistic. So yeah, we use fractals to simulate the substructure, the spatial substructure within the star-forming regions. And these 6 here are just examples of some of my very fractal, very clumpy simulations of dense bound clusters. And it's the fractal dimension that we use to describe and determine how clumpy a cluster is, where a lower number, so a lower fractal dimension, means that it's more clumpy. And there's evidence that the sun may have formed in a cluster. So that's one of the reasons why it's going to be quite realistic to simulate something that looks a bit like this initially. So I'll move on to talk now about sort of one aspect of my research, which applies particularly to the solar system and where we think the solar system might have formed, and that's whether there's a stolen planet in our solar system. So Planet 9 is a hypothetical planet that is thought to be around 10 Earth masses if it does exist, and it would orbit really, really far out in the solar system. The evidence for its existence is basically just these Kuiper belt objects or asteroids that are shown in white here. You can see that their orbits are all quite correlated and clustered together, and if you were to view it on its side, they'd also be clustered together in their angle of the inclination to the plane of the solar system as well. And this clustering, since it's quite unlikely that it would happen by chance, could instead be explained by the gravitational effect of Planet 9, so around a 10 Earth mass planet orbiting in this sort of orbit here. However, if it does exist, in order to fit and explain those asteroids, its orbit would have to be quite unusual. Excuse me. So as I was saying earlier, planets form in, sorry, I'm gonna have to have a drink. planets form within the protoplanetary disk of gas and dust that orbits a star. So this diagram here, all of the distances are to scale, but obviously the size of the sort of planet and star isn't. So although these disks can extend quite far out, it's only actually really in the sort of centre and close regions of it where there'd actually be enough mass to form a planet-sized object. So this sort of distance here is really the farthest away that you'd expect a planet to form. So planet form must have formed sort of here, but actually it's all the way out here up to around 1000 AU, so 1000 times the Earth's sun distance away from the sun. It would also have to be inclined to the plane of the other planets by around 30 degrees, which again, since the disk is quite flat, you know, there's just no material up here for it to form. And you'd also expect its orbit to be circular if it formed in the circular disk, or at least just not very eccentric. But actually it would have to have an eccentricity of around 0.6 and something like that, rather than anything close to a circle. Obviously, and I personally think that perhaps explaining a bunch of weird orbits by introducing another weird orbit isn't perhaps the ideal sort of solution to the problem. But when you look historically, most new solar system objects have been discovered just by looking at existing orbits, seeing that they don't make sense in some way, and then looking for a new object to describe that. So that's why it's definitely something that's worth investigating and searching for, and there's actually 2 teams that have been looking for it for quite a while now. So if it does exist, this all means that Planet 9 can't have formed where it is currently observed. Well, not observed, but where it currently would be. So the question then is, how did it get there? There's sort of 4 options for this. The first would simply be that Planet 9 formed in the inner solar system with all the other planets, and that it was just disrupted by the other planets in the solar system. There's already some evidence that Jupiter in particular did this to potentially a 5th giant planet in the solar system that was flung out. So because there's already evidence that this probably did happen in the early solar system, perhaps wouldn't be weird to expect that this happened. It's also possible that Planet 9 could have been disrupted by a passing star. So again, that would be forming in the solar system where you'd expect it with all the other planets. But then, like I said, there's some evidence that the sun did form within a cluster like that. So you'd expect for it to not be uncommon that other stars and bodies were passing by the solar system, and that might have disrupted Planet 9's orbit and flung it out a little bit. It's also possible that it could have been captured from free floating. So for this to happen, So for this to happen, Planet 9 would have had to have been initially ejected from its original system. Then it would have been a free-floating planet, just sort of travelling around the cluster. And then if it came across the solar system gravitational pull could have pulled it in and got it bound onto an orbit, although obviously an unusual one, because for that to happen, there's no real reason for it to be on an orbit that's circular in the plane of the other planets or close by. Or the final option, which is sort of the main focus of this bit of my research, would be that it was stolen. So I'll just move my finger out of the way. That's shown in this diagram here. So for a planet to be stolen, it's different from capture because the planet would not have been free floating for any period of time. You can see, so we've got the planet and its original star, and as they pass by each other in the cluster, at the point where the gravitational pull from the stealing star, which would be the sun in this case, was bigger than the gravitational pull on the planet by the original star, the planet can just go directly from one orbit to another and then travel off with its new stealing star. This can happen either if the stealing star is more massive than the planet's original star, so it has a bigger gravitational pull that way, or if a planet is initially just disrupted in its original system, so it's on a bit of a farther out orbit, it then might be a bit more likely that a new star can come and pass close by and steal it from its original one.
I think you went too
Keep
far.
doing that, sorry guys. So my simulations, like I said, there's evidence that the sun may have formed in a cluster. So that's in the form of isotopic ratios, so radioisotopes that have been seen in the solar system in sort of meteors and things like that. And they imply that the early solar system was probably quite close by a supernova. And for that to be something that's very likely to happen at all, the sun would probably have had to have been in quite a dense cluster with massive stars that were close by. So it then makes sense for us to run Nbody simulations, like Christina was talking about earlier, where everything's just a point mass of these sort of clusters. So I run those simulations of the planetary systems in the star clusters, and I run them for around 10 million years to see what happens to the planets in them. So with the initial conditions that I've got shown here, that's around 1,000 stars, all within around 1 or 2 parsecs. So again, that's sort of the distance from the sun to the closest star to the sun. 500 of them have Jupiter mass planets placed at 500 AU. Obviously, I said earlier that if Planet 9 exists, it's probably around 10 Earth masses, but we wanted to run some simulations that were quite generic and could just apply to generic planetary systems, so that's why we chose a Jupiter mass and 50 AU. And again, they're very clumpy, very fractal to begin with, although that very quickly changes in like the video that we showed you earlier. So for each set of initial conditions, like these ones here, I run multiple statistically identical realizations of them. And that's because although all 6 of these are all statistically identical, you can obviously see that they're visually just very different. So different things are going to be happening in them. And that's just because although they have the same fractal dimension, making them statistically identical, a different random number seed has been used to initialize the fractal. So it's important to sort of add them all up to average out any differences that can come from that. So these are my main results here. On this plot, sorry, trying to get rid of my zoom thing. I've got the semi-major axis on the bottom, which is the average distance from that a planet is from its star, and that's measured in AU, so Earth-sun distances. Just for reference, we've got the orbit of Neptune here, so around 30 AU, and then Planet 9's predicted orbital range of around 400 to 1,000 AU. And then the semi-major axis of the widest observed exoplanet here at around 1,000, 1,500 AU. And these will be the semi-major axes of the planets after 10 million years for 15 of the realizations. Then on the y-axis, I've got the eccentricity. So that goes all the way from a circle all the way up to a planet that was sort of off the graph, would be unbound from its system.
Your mouse is not visible.
Oh, that's because thank you. It's because I moved the zoom thing around.
You need to go one back, I think. One slide back.
I'm sorry, guys. Thank you.
Trying to make everything visible at the same time while controlling my computer.
Okay. So I have the preserved planets as the grey dots, and these preserved planets are ones that at the end of the 10 million years are still orbiting their initial star. But obviously, as you can see, their orbits might have been quite disrupted by passing stars and planetary systems that have changed both their semi-major axis and the eccentricity. Then I've got planets that have been captured from free floating as the blue crosses, and planets that have been directly exchanged or stolen between stars as the orange stars. So just in terms of the number of these different sort of planets after 10 million years, around 40% of them are preserved and still bound to their star at the end, which in of itself, even though it's not actually what I'm looking at, is really interesting because it shows that it's all like 55% of the planets after 10 million years aren't even bound to a star, even though they started off that way. So that just shows sort of the frequency with which planetary systems are disrupted. Then we get around 5% of them are stolen and around 2% of them are captured. And you can see from looking at the plot that a really significant amount of planets on wide orbits beyond around 100 AU. So this is beyond really where you'd expect a planet to be able to form out here, are stolen. And planets can be stolen onto orbits sort of in this range that are consistent with Planet 9's orbit. However, once you get a bit further out, so onto sort of the widest exoplanets and beyond, these planets are much more likely to be captured than stolen or preserved. So just to summarise my results, interactions between passing stars can change planets' orbits. There might be another planet in our solar system in the form of Planet 9, and if it does exist, it might have been stolen or captured from another star. So I'll pass on to Christina now.
Thank you, Emma. So I hope everyone can see my mouse properly. So we're now going from planets being stolen by the sun and maybe orbiting around in the solar system, to looking at something very different, to looking at ejected stars. I've briefly shown you these stars in a simulation earlier that are things that get thrown out by the clusters during their dynamical evolution. And the majority of my work as a PhD student actually look at what and if these ejected stars can actually tell us anything about the star forming regions where they come from. Because we don't really quite yet know everything there is to know about star forming regions when they were forming. And the question that I was given at the beginning of my PhD was, can you look at stars that are no longer in the cluster, and can you see if they tell us anything about the region where they come from? How do we find fast ejected stars? Of course, the first question: what are ejected stars? Is there any definition? Is there any kind of background to these kind of things? And they were only discovered in the 1950s, so they haven't been around for quite that long yet. And they were termed very early on as runaway stars in 1961, because of course it perfectly explains what these stars do, because they run away from their birth cluster. And originally these stars were described as having a peculiar velocity above 30 kilometers a second. It was even 40 kilometers a second at the beginning. However, this velocity boundary is actually not based on anything physical that suddenly happens at this velocity boundary, but this boundary was chosen based on the results in early observations that only at this velocity was it actually possible to tell apart runaway stars with other stars that just had very large errors. So in order to be sure that these stars were actually a distinct group from other stars that were still in the cluster and just misidentified, a boundary of 30 or 40 kilometers a second was put on the earlier runaway stars that were found in the night sky. Since observational technology has moved on since the 1950s and 1960s, we are actually now convincingly finding slower ejected stars that are also called very descriptive name, which are called walkaways, because they walk away from their birth region. Regardless of them being walkaways or runaways, the only difference that they have is actually the velocity. The mechanisms that cause their formation is actually the same. They're just two distinct, not too distinct, they're two different stars at different velocities that we can see in the night sky. Originally, it was thought that runaway stars would always be big and bright stars, because of course, back in the days, it was easier to observe big and bright things, especially moving at fast velocities. However, my research and other research has actually shown that any star has a potential to become a runaway star in a cluster. We see here on the right a picture of a simulation after 4 million years, where we have the roughly spherical centralized cluster at the center. We have two red high mass stars having been ejected, and loads of lower mass stars, which are much more prevalent in star clusters, also been ejected. So in order for us to get a really big and complete picture about the population of ejected stars, we should look at both the big stars and the small stars to see if there's anything that is different in the population depending on different initial conditions, so the different setup in the simulations. Before we get to that, I'm just quickly showing you an animation of two of the two main explanation mechanisms of how to make a runaway star. One is the dynamical ejection mechanism, which is the one that can explain ejections regardless of the age of a cluster, because there's dynamical interactions between stars in a star cluster at any point in time. It is not reliant on other physical phenomena. It's just the interaction of two binaries here that come in close contact to each other, and they start interacting with each other they start as they exchange stars, and at some point the blue star, which is the lowest mass star, gets ejected from these two binaries, and we have a very tight binary with a third star on a wider orbit around this one. So this is one of the explanations of how we get runaway stars. A second explanation, or a mechanism that is used or is known to create runaway stars and walkaway stars, is the binary supernova mechanism. It's in the word. This mechanism requires a supernova, so it requires a star that is above 8 solar masses to begin with. These stars are often found, or almost 100% of them are found in a binary with a lower mass star together, and then evolve together over time. Eventually, the big red star here goes supernova, so it explodes in a very energetic explosion, and this can disrupt this binary and shoot off the blue star as a runaway or a walkaway star. Also, the supernova remnant can become a runaway or walkaway star, which we see briefly here running away. But what's left after supernova is either a neutron star or a black hole, and these are much more difficult to observe compared to a main sequence companion star moving across the night sky. The supernova mechanism can also not be used to explain ejected stars in very young star clusters, because the first supernovae usually go off after 4 to 5 million years. So only after this time can this mechanism actually come into play. And we also don't see many supernovae in star clusters, so they cannot create the large population of ejected stars that we can find around young clusters. So now we look a bit back into actually my work, looking at what do Nbody simulations predict. My work is about trying to figure out if ejected stars can tell us something about the star cluster they come from. And what we see here are selected results from 2019, from last year, where I look at a cluster that starts its life very clumpy. We have seen what clumpy means in Emma's pictures of her simulations. And with this clumpy spatial substructure, I'm actually trying out 3 different initial virial ratios. So the kinematic substructure is different in these 3 simulations. I have simulations that already start off in virial equilibrium, and then 2 other simulation setups that start getting more and more subvarial. So less and less kinetic energy is in the cluster, which causes the cluster to collapse rapidly and then expand afterwards when the cluster is trying to achieve virial equilibrium. The yellow line here are the bigger and brighter stars that become unbound over time. We're shown here the first 10 million years. And the red stars are the smaller and fainter stars, also as they become unbound, as a fraction of the total population in this mass class. And what is becoming quite obvious is that there is a difference between these selected scenarios. We can see that the more in equilibrium a cluster is originally, the higher the unbound fraction, the ejected fraction of lower mass stars. So around a cluster that started its life in this original setup, we should find a larger proportion of its stars unbound from the cluster. Whereas something that started a lot less in equilibrium would actually not kick out all of its lower, such a large proportion of its lower mass star. On the other hand, we see the higher mass stars, the fraction actually reduces the more a cluster is initially in virial equilibrium. So in simulations, we can see that ejected stars can help to actually constrain the initial conditions, to limit the initial conditions of clusters. So the question is now, can we actually see any of this in observations, or is this based on models, theoretical models that are not correct? So in order to see if the simulation actually predict anything that we can find in reality, I use observational data as well. I'm using observational data from Gaia, which is an observational telescope that orbits in space around the Earth. It has been launched in 2013 and has been observing the Milky Way continuously over these many years, taking data on the position and the motions of over 1 billion stars that are surrounding us continuously to a very great accuracy. And the brilliant thing about Gaia data is that it's very easily accessible. So there is an archive. It's easy to look up any kind of star that emits in the optical wavelength range. So Gaia is an optical telescope, so it won't see stars in the infrared or in other wavelengths. It will only see stars in the optical. But it's such a vast collection of data, and it's a great source for information about position and motion of stars. My first observational target is the Orion Nebula cluster, which is a really well-researched cluster. So it's a really great test bed for my work, because there are quite a lot of things that are already known about this cluster. The average age is known. We have a good idea of how it looked like when it started with regards to its initial spatial and initial kinematic structure. So using this cluster as the first test object to see if we can, or if I can find runaway and walkaway stars around it, and see how the numbers and the velocities of these stars compare to my simulations, is actually a great way of testing the theory behind the simulations. We can see here Orion, the constellation Orion's belt, and the ONC is below the Orion's belt. If we zoom in further, we can see there's quite a bit of gas and dust, and only about half of the 3,500 to 4,000 stars that are in the ONC are actually only visible to Gaia. The other half only emits in the infrared because they're obscured by the gas and actually do not show up in Gaia. So we can only see half of the stars of this cluster. But for my work, it doesn't actually make much difference, because I'm not interested in stars in the cluster. I'm interested in stars that are no longer in the cluster, so that have actually passed the boundaries of the cluster. This is a picture of all the data points that you can get when you look at the ONC. This is the ONC, the little yellow dot at the bottom, and stars, all the data points that Gaia has in 100 parsec around it. I think there are about 250,000 data points in this plot that are all the stars that are surrounding the ONC within 100 parsec. And what I did, we have the motion of these stars around, and we can actually trace back these motions and see if any of the stars that are surrounding the ONC actually move away radially from the ONC. We see here the red arrows are the stars that move at runaway velocities, so they're the faster velocities. And the blue arrows are the ones that move at walkaway velocities. We can see a large number of stars moving away from the cluster, but this is only in one 2D dimension. We can also do this in the other 2D planes, and only if a star traces back to the ONC in all 3 dimensions is it possibly a candidate. However, just because a star traces back to the ONC doesn't actually mean it's born there. It could be just coincidence that it's flown through the ONC at one point in time, and we just observe it to trace back to the ONC, but it was not actually born there. The ONC is a very young cluster, so most of its stars have not actually reached the main sequence, which you remember from earlier in the talk is this band that goes all the way through the color magnitude diagram. On the right here, we see actually the color magnitude diagram of these 250,000 stars that are surrounding the ONC. And we can see the main sequence coming out fairly clearly. Down here, there's measurement errors where even Gaia gets things not quite right. This is why there's quite a blob here. What is still shown clearly here is the white dwarfs at the bottom. And we can see other aspects of the main sequence is the main sequence turnoff, which is the evolutionary direction of stars like the sun. You can see this also here in the data point. The main sequence, as I mentioned, is where stars spend most of their time, but most of the ONC stars have actually not reached the main sequence yet. They approach the main sequence from this direction, and stars that are younger than the main sequence that can possibly have been born in the ONC are located above the main sequence. They're located around here. If we plot all the candidates that trace back in 3 dimensions to the ONC and lay something called an isochrone, which is a line of the same age all the way through, we can see here that all the way up to here, 4 million years as the upper age limit for the ONC, we can see that only the brightest, most massive stars will have actually already reached the main sequence. Anything that is younger than that is less bright than that will actually have not yet reached the main sequence here. Any star that is located above the isochrone is highly likely a star that actually was born in the ONC, as its age is consistent with being young enough. However, we found quite a few stars, and we can see the little X's and crosses here, of stars that are just coincidentally flying through the ONC, but are already along the main sequence and therefore already too old to have been born in the ONC. If we look at the findings at the end, I find 9 runaway stars, so 9 of the fast stars that are young enough to come from the ONC and that trace back to the ONC, and 24 walkaway stars that do the same thing, that are young enough and trace back to the ONC. And I did compare these numbers to my simulations to see which of my simulation setup with different initial conditions will actually match these numbers. So can I find out something that is very different to what was predicted in other surveys about the age and initial substructure? But interestingly, my results confirmed the average age of the ONC between 2 and 3 million years. Because after 2 to 3 million years, the amount of runaway stars still within this region is the same in my simulations compared to what I find in observations. And also my simulations match the results when we look at the substructure, the initial substructure. So by using the ONC in observations, I've actually found observational proof that ejected stars can tell us something about the initial conditions of the ONC. And I'm now handing back to Emma for final remarks.
So just to summarise, we started off by talking about how stars and planets form together in star-forming regions that can be dense enough for the other stars to affect the planetary systems. Then I spoke about how interactions between passing stars can change planetary orbits, and that there might be another planet in the solar system in the form of planet 9, and that if it does exist, this might actually be from another star, so it might be an alien planet. And then Christina spoke about how ejected stars give clues about the initial conditions in star-forming regions, and how we can analyse those stars using simulations and search them in observations to find new things out.
Thank you.
Thank you very much.
Would be questions, because yes, we're at the end.
Thank you very much, ladies. That's very interesting. Now, the way we usually do questions is I ask you to turn off your presentation and return us to gallery view. And then I'm going to ask people to put up a digital hand or wave at me, and I will nominate them. Okay,
turned off the presentation.
Okay, so I can see everybody's face, and hopefully you can see everybody's face as well.
Yes.
So whilst I'm waiting for people to come up with questions, I've got one myself. Emma, you mentioned that you suspect that 55% of all planets are unbounded to a star and just floating around loosely. Did I get that right?
So Depending on who you ask, someone would say yes, the majority of planets become unbound. But I think so those simulations are probably the most dense sort of star cluster, and you definitely expect that there's also a lot more planetary systems that form in clusters that are less dense, and then there'd be less interactions and they'd be less likely to fly out. But I think the estimations for free floating planets range from them being as or more frequent as just stars like the sun, or being around sort of 10% or a bit less as common as stars. So there's a big...
Okay, thank you. So firstly, Tony Morris, can you unmute yourself, please?
Hello, Paul. Can you hear me?
Yes,
I've got a question.
your question, please.
Question for Emma. Emma, you mentioned in the presentation about the fractal dimension of the star clusters. Certainly for like people who've messed about with Mandelbrot's and Julia sets at home, the actual formulas are very, very simple. So how do they scale up for something that's effectively a three-dimensional body that's not in a flat plane, is my question.
So for the sort of box fractals that I use, a fractal dimension of 3 is sort of just totally homogeneous, just an evenly distributed sphere. And then a fractal dimension of 1.6 is kind of really, really fractal, like the ones that I've shown you. Is that what you're asking, or have I got the wrong end of the question?
I wasn't asking about the fractal dimension, just so, you know, the programs that you can run on your smartphone or your computer, if you look at the underlying equation, it is really, really simple. But it's actually just on a plane, on an XY plane. But obviously your models are three-dimensional.
Oh, I see. No, yeah, it's still really simple. I wouldn't know off the top of my head, but it's, you know, it's no more than a few terms. It's very simple. And that's why fractals are used so much for this sort of research. There's other models that you could use that would take a lot more sort of computer time to run, but it's because the fractals are so simple that they're really useful.
Okay, right, thank you.
Thank you, Tony. Peter Lloyd, please. Can you unmute yourself?
Yes, thank you, Paul. Yes, I think I understood you to say that most stars are formed as part of a cluster. Is that right?
Yeah.
Okay. Now, in that case, the sun was probably formed as part of a cluster, and I'm wondering whether it's likely it was a runaway or walkaway star, or is 4,000 million years enough time for a cluster to disperse more naturally?
That's definitely enough time for it to disperse naturally, but I think Christina would probably know whether it might have been.
Yeah, this is kind of the question I always think about. Could the sun have been a runaway or walkaway star? But the age of the sun, because most of the clusters kind of disperse into the field after 10 million years. So like I think 90% of the cluster don't really survive their first decade of million years, and they kind of disperse already. And at some point, they kind of get swept away by the tidal field of the galaxy. And it's really difficult for something as old as the sun to even trace something back, because it has been going around the galaxy for so long. And I think there's attempts to figure out the origin cluster of the sun. It might have just been dispersal into the field and not been subject to a big ejection, because it still has quite a lot of its planets. And to be ejected, it has to undergo quite a lot of dynamical interaction, or supernova possibly, as Emma mentioned. And I personally think as a runaway, it might have not kept hold of all of the planetary system as quite of nice and neatly arranged as it is now. So I don't think it's a runaway personally.
So you think that it's probably just the cluster dispersed thermally, as it were? Yes.
Yes, I think so, because it's kind of, the cluster itself, they can survive the first supernova if they're lucky, but often the supernova just kills the cluster altogether, the first or second supernova that goes off. Or it kind of disperses into the field just because the stars get picked off by the tidal field of the galaxy, and after so many billions of years, the cluster, you can't even trace it back anymore, because there's so many interaction. Any interaction changes the path of a star or any object.
I can understand that if they normally disperse in about 10 million years, 4,000 is going to be impossible task. Thank you.
Yeah, definitely.
Thank you, Peter. Roy Gunson.
Hi there. Just a couple of points I've got. When you were talking about clusters, I'm presuming you're talking about clusters like, say, the Pleiades or the Hyades, and not globular clusters like, say, M13 in Hercules, the really massive things.
Yeah.
But I presume the runaways and ejected stars would still apply to things like globular clusters.
Globular clusters they are at the opposite end of the age scale. So the young star clusters are the really young stuff, and the globular clusters is all the old stuff. They're massive as itself. I don't think there's quite as much dynamical interaction between the stars. There's definitely, or it's unlikely to be that many supernovae going off anymore. I don't know if they're actually there might still be ejected stars from these kind of clusters as well. But I don't really know too much about ejected stars from the old globular clusters to be able to say anything. But any kind of dynamical interaction can cause something to get ejected. But in order to get kicked out of a globular cluster, it has to be extremely energetic, because of course the masses of those clusters, the potential energy is just so much bigger. Because I think they have 10,000s of members, or even higher number of members, and they're even more massive than some of our supermassive younger clusters.
The other point I was thinking about was, talking about planet ejection and occurring in clusters. Well, as the sun moves around the galaxy, it actually does get closer to other star systems during that process. I mean, I believe the star system Algol was within about 6 or 7 light years of the solar system, and that's about a mass 8 system, which would have had certainly an effect on the Oort cloud region of the solar system when it passed by. So I mean, in 4 billion years, I mean, certainly would other stars other than cluster stars would have probably come close to the solar system and given an opportunity to maybe transfer planets one way or the other.
Yeah, so I mean, although very, very unlikely, it could definitely happen. For those sort of things to happen that definitely disrupt a planetary system, they come within sort of like 1,000 AU, or even within hundreds of AU or Earth some distances to the solar system. But you can also have sort of slight perturbations that don't immediately eject a planet, but they just sort of set the planets off destabilizing each other, and then over millions of years afterwards it can get ejected. So yeah, I think probably very, very unlikely, but it is possible.
Okay, Roy, has anybody got any questions? I'm not getting any more blue hands.
I think I lost sound. I don't know if anyone else.
Yeah, Paul's on mute.
Ah.
It's all right. It's all right. I forgot to put my
talking.
Yeah, Baby Starman, Mike Popson, can you?
Yeah, hi. I have
your question, Mike.
Right. Yes, it's a question about a specific star that I've just had a paper published on. The star is called V1117 Hercules. Basically, it's a Habe. It's a sort of a high mass T Tauri star. The strange thing about it is it's 36 degrees above the plane of the galaxy. It's traveling towards the galaxy, so it's been created even further out, basically where there are no star-forming regions. And I'm just wondering what can be going on. Really, whether the ladies have got any idea. It's not specifically a runaway star, but it's just coming from an area basically where it shouldn't have been formed.
Yeah, as a Herbig star it was it high mass Tauri?
Yeah.
Yeah, so it's still really young, so it must have formed not long ago. So it really depends on the kind of velocity. I don't know the star in particular, but the question is if there's anything, because we know that other stars from other galaxies or other regions are visiting the Milky Way. So this is like some of the results that also Gaia has shown, that there are actually stars coming from other regions. But of course, as a Herbig star, it has been probably has not been flying for quite that long.
It's not very old, no.
Yeah, and the question is if there's any way to trace it back to, or how far it would have flown or where it might come from. But it's an odd one, having such a young star, because it should come from a star-forming region, because all by itself, it's much more difficult to form, I think.
Yes, exactly. And as I say, it's actually travelling from further above the plane of the galaxy. So, you know, it was formed further out than where it is now. It's a very peculiar object. It shows sort of dips roughly about every 400 days. It's basically a UX Orionis star. And we think the dips are due to its being occulted by some circumstellar material. So it's, you know, it's still in the process of sort of disk formation, or at least planet formation. Yeah, but as I say, it's coming from a place where it shouldn't have been created. It's a very, very peculiar object. Yeah, I suggest you Google it.
Yeah, but what is the name again? So I just can see.
It's V1117 Hercules.
I'll have a look at that, because that is interesting.
Yeah.
Sorry, I was just saying, do things ever get ejected and then get pulled back and go sort of like in a U shape? Like, could it have been? I'm not sure whether that ever happens.
Well, assuming, well, I say assuming that it was formed in a star-forming region. I mean, that's not really a very good assumption, because it obviously wasn't, because it's actually it's travelling towards a star-forming region. As I said, the galactic latitude at the moment is about 36 degrees. It's 36 degrees north of the galactic equator, you know, a very, very long way from any star-forming region. And it's actually being born from even further outside, because it's travelling towards the plane of the Milky Way. Yeah, so obviously it's not strictly a runaway star, because it's got a very modest kind of space velocity. You know, but it's still doing the sort of thing that really shouldn't be doing, according to theory.
That's an interesting one. I don't have any.
No. I just thought, you know, you might have some idea of because nobody else has. So yeah. If you Google that, you'll probably find out quite a lot about it.
No. I just looked at Simba to just have a bit of information about it, and it looks like it has some Gaia information as well, which of course is always helpful.
Yeah. Good. Are you using the Gaia data release too?
Yes, always.
Yeah.
Always DR2.
Oh, cheers. Cheers anyway.
Thank you, Michael.
Thanks
so Chris again.
A general question on these high velocity stars that are ejected from clusters. Is there a possibility that they could be ejected from the host galaxy? And if so, do they orbit the host galaxy, or could they just be intergalactic wanderers?
Well, stars that are ejected from the galaxy itself are called or hypervelocity stars, and in order to escape the galaxy itself, most of these stars actually interact with the supermassive black hole at the center of the galaxy. So they don't necessarily, in order to escape the galaxy, they have to get really, really fast. And most of the dynamical interactions in star clusters are not energetic enough to actually accelerate them out of the Milky Way. But I think there are about slightly more than a handful known hypervelocity stars that actually get accelerated fast enough once they pass the supermassive black hole in order to leave the galaxy. And if they're unbound from the galaxy, they will actually get kicked out and might visit another galaxy. Like we have visitors from other galaxies as well. So Gaia has found actually visitors from another galaxy that actually visiting the Milky Way, because they got kicked out from their host galaxy as well. So
okay, thank you.
they're really, really fast, and they normally need the supermassive black hole to get this fast, to get kicked out. And there are not quite that many known about them. I think there are a handful that are confirmed, but it's a slightly different mechanism than you can get in star clusters, because they are not massive enough. They're not dynamical enough to get that.
Okay, thank you.
Yes.
Okay, Peter.
Right, hi. Is there any evidence of Planet 10? I mean, the object which is supposedly at the edge of the Kuiper belt. Apparently the Kuiper belt ends abruptly about 55 or something like that astronomical units. It's about up to the size of the Earth, or mass of the Earth, that is. Has there any search been going on for that?
Yeah, it's actually, there's two groups looking for it, and they've been doing it for long enough that it's starting to look like if it does exist, it has to be even farther away than they thought. Yeah, there's two separate groups looking for it. The idea being that they each independently look over every sort of bit of space where they think it might be in case one of them misses it.
Yeah.
It's just a bit awkward because it just always might be more massive but farther away.
Yeah.
So there's not really sort of a concrete sort of time when you should stop looking for it and say it doesn't exist.
Yeah.
So I'm not too sure how much longer they'll go on.
Okay, cheers. Thanks.
Okay, ladies and gents, I think we have worked Christina and Emma really hard this evening, and in our usual Mexborough and Swinton Astronomical Society manner, can we give them a big thanks?
Thank you.
Thank you.